Dear students, welcome to my YouTube channel. I, Professor Prashant Bua, Dr. Subhash Technical Campus, Junagadh. Today's our subject is Design of Reinforced Concrete Structures. Topic same, Earthquake Resistance of Building, Lecture 3. So in previous two lectures, we discussed about the earthquake resistance design all building and philosophy of earthquake resistance towards the resisting our structure, how we can possible with the new techniques to provide the earthquake resistance. Today in this lecture, it means lecture 3, still we continue the earthquake resistance building regarding the important aspect of inertia force while earthquake is occurring on building. What should be the effect of deformation of structure and what should be the effect of seismic inertia force. That all forces are discussed in this video lecture. So start with the what are the seismic effect on structure. So first of all, inertia force in a structure. So earthquake cause shaking on ground. So a building resting on it will experience motion at its base. From the Newton's first law of motion, even through the base of building move with the ground. But the roof has tendency to stay in original position. But since the all walls and column are connected they drag the roof along with them. This is much like situation that we face with when the bus you are standing in suddenly start. Your feet move the bus, but your upper body tends to stay back, making you fall break down. So this is the tendency to continue remain in a previous position is known as inertia. So we all know that the effect of inertia in our day-to-day life. So in a building, since the wall or column are flexible, that we know that the motion of roof is different from the ground or shake. We will see in this figure. You can see that this is the stable house. When the earthquake is shaking, you can see that next image. When the earthquake in this direction, our slab is fixed, column and beam are fixed, but our roof is move opposite on a direction of earthquake, and that should be a very effect of inertia force while shaking the ground, and the building is move opposite on a ground or earthquake force. This is nothing but the effect of inertia force in structure, and while the earthquake is measured, that effect should be more in our structure. Next, consider a building whose roof is supported on column. Coming back to the analogy yourself on the bus, still again you have to analyze your example with the same bus, and we have to consider whose roof is supported on column. Only the roof is supported on column we have to consider and get the next example. So thinking your mind, you are in a bus, suddenly it should be start. You are thrown backwards in someone has applied the force on the upper body. Similar, when the grounds move, even the building is thrown backwards and the roof experience of force called inertia force. That will be seen in previous figure. If the roof has mass m, now you have to note it down, take roof mass as m and experience an acceleration from the Newton's second law of motion. The inertia force is denoted at F1 is mass m times acceleration is denoted by a, and its the direction is opposite to that the acceleration. The clearly more mass means higher inertia force, and therefore lighter buildings sustain the earthquake shaking better. That's why we get the design of building are as much as lighter, so that this inertia force are not effect in our building. So this is the main aspect. Here you can also note it down. Therefore the lighter building sustain the earthquake shaking is better. This is our key point of this structural situation. So now we take the second figure that will be create in your mind, that the soil should be rest, foundation should be rest on soil. You can see that foundation is fixed. the column are attached with the foundation and roof. You can see that a roof take the mass M and column is attached with the foundation. Now acceleration for S, it should be travel on this direction of figure. You can see the inertia force are always in opposite direction of this acceleration force. You can see in this figure. So what should be the done? If the building is stable, there is no inertia force. While if the inertia force is occur, you can see the effect of column. It should be start to the buckling and roof should be transferred to the opposite direction of inertia force. This deflection or inertia force move in original position is denoted as U, is nothing but our work done when the inertia force is acting. So this is the very clear picture while the inertia force acting in our building. And if still doubt, then in your mind, took the example of bus when you have to sudden stopping and sudden starting of bus. So this is all about the inertia force, relative motion with a building. Now effect of deformation in a structure. So the inertia force experienced by the roof is transferred to the ground by the columns. So causes force in a column, this force generated in the column can also be undergo in another way. So during this earthquake shaking, the column undergo relative moment between their ends. We all know that column are fixed. One end fixed as a foundation and one end fixed as a beam column slab. So both the end are fixed. So there have the relative moment between their ends. So this moment is shows a quantity U between that will be seen in previous figure and roof of the ground. But given the free option, the column would be like compact and straight a vertical position, like column resist the deformation. In straight vertical position, the column carry on not horizontal earthquake force through them, but when the force is tied to the bend, they develop the inertia force, and the larger is relative horizontal displacement between U and the top of bottom of column, the larger of inertia force in a column. That's why that again we have to discuss about our first lecture, energy releasing principle, or you can say strain energy principle, elastic rebound theory. Up to the column, they have the sufficient resisting power of the deformation. You can see over that. So column is resist the deformation in straight, but when the column is tied to the buckling, or it should be a loose, the elastic strain energy system, then it should be create a displacement is denoted by U, and that will be seen in our previous figure. I also repeat this figure. You can see that this is the acceleration force A, inertia force towards the opposite direction, and you have to rotate down the U. U is nothing but our displacement at horizontal of top, and that is the effect from our column beam column joint why the deformation of structure is affect. Now flow of inertia force to the foundation. So under the horizontal shaking of ground, horizontal inertia force are generated at the level of mass of the structure. Usually this situation at the floor level. This lateral inertia force are transferred by the floor shape and wall of the column or to the foundation. So the load transferring system is floor shape to the wall or column, and column should be transferred to the foundation. So finally soil system undergoes the effect of this force. So each of these structural element like floor, slab, wall, column, beam, foundation, and the connection between them must be designed to safely transfer this inertia force throughout them. So this is the hierarchy of load transferring system. Same hierarchy will be done while the inertia forces occur. So our elements of structural and joint between them are very much sufficient to take this inertia force, and then it should be transferred to the soil, and after that soil should be resist this inertia force. So it's very important our elements design should be proper to resist this inertia force. Again you can see that figure. Our soil should be move on the earthquake direction of shaking. You can see that foundation are different role play. our wall or column are different wall prey and inertia force. You can see that direction of inertia force worked with earthquake shaking. It should be opposite in earthquake shaking. So it should be a very severe effect while the earthquake shaking on building. And that's why in previous the earthquake should be occur in 2001 on Bhuj. We neglect the effect of load bearing structure. So generally we construct, if the high rise building or G+2, generally we prefer the column frame structure with the column and beam. So it should be resist very easily to our load transferring system. So this is the flow of seismic inertia force through the structure. So what should be our main focus? When the earthquake it should be occur, our inertia force should be stand for slab to the slab transfer to the column transfer to the foundation, and foundation should be transferred to the soil. So this hierarchy are not damaged while during the inertia force is occur. Then and then our building is stable against this inertia force, and it should be resist the earthquake shaking effect. So that's why our all the elements of RCC are sufficient to resist this earthquake shaking force, and it should be stable against the inertia force also. So the wall or column are the most critical element to transferring the inertia force, that we know that, because that alignment of wall and column are vertical and our forces should be horizontal. That's why it should be most critical element while transferring the inertia force. But the traditional to construction floor slab beam receive more care attention during the design of construction, and then wall and column. So the wall are relatively thin and often made by brittle material, that we all know that wall made by either brick or stone. So it's like a brittle material compared to RCC. So there are poor carrying the horizontal earthquake inertia force along the direction of their thickness. So the failure of masonry wall have been observed in many earthquakes in the past. Similarly, the poorly designed and construction reinforced concrete column can also be destroyed. So the failure of ground story column result in a numerous building of collapse during 2001 Bhuj earthquake. So that's I discuss about that previous, when the 2001 Bhuj earthquake are occur. Lots of our construction mistake, or you can say the design mistake, are seen in this earthquake should be occur. So first one, our masonry are not well designed, or we can neglect that effect of wall. So we doesn't about the proper design while the wall is constructed. So that's why it should be create very severe effect in earthquake. And second aspect, our RCC work are not properly designed as per our horizontal force resisting, and that's why the code should be revised, and we have to introduce this earthquake resisting force, because that should be a horizontal and our alignment of frame is vertical, so it's completely resist this force. So there are lots of similar poorly design are seen in this 2001 earthquake should be occur. We will see this figure. You can see the first figure, partially collapse of stone masonry wall during the 1991 Uttarkasi, India earthquake. You can see that the roof is tendency to not resist any types of load, so it should be stable in that condition. It should be, you can see that slab is not fell, but our wall is fell during this earthquake force. Now you have to take second image, the collapse of reinforced concrete column and building during the 2001 earthquake in India. This is the severe effect you can see in this building. Now this is the only the load bearing structure, that's why the wall should be failed. Now here second is RCC, and then also it should be cell. Why? Because this is the effect of inertia force. While the earthquake it should be shaking, inertia force in opposite direction, and our building is not a load transferring system to the our substructure, and that's why it's you can see that it should be a collapse in between the building. So this type of effect are neglected in our design. Before we casting any RCC building, you must be worried about the earthquake force. So these both figure are comparison about the importance of design of wall and column. How much the importance in a building are same as column, RCC, wall, and our different element are important for the earthquake force is resisting. Now, how the architectural features affect the buildings during the earthquake. So the importance of architectural feature we kept in mind not only the RCC design as well as the elementary of beam wall are that much important, but our building shape, size and the heights is also important for the aesthetic point of view, or you can say the architectural features. So desire to create the aesthetic of functionality efficient structure drive the architects to convene the wonderful and imaginary structures. So sometimes the shape of building catch the eye of visitor. Sometimes the structural system APL and the other oscillation, both the shape of structural system work together to make the structure are marvel. So what should be the role of architecture? That we all know that should be create the more innovative and effective shape that should be a visitor in your eye, and it should be create one image. Wow, that shape is should be perfectly. But on the same time, it may be not proven by the structural designer also. So however, each of these choice of shape structure has significant bearing on the performance of building during the strong earthquake. So you cannot given the shape and size of building before to visualize the earthquake force. That's why it's very important to resist this strong earthquake. What should be our building shape? So the wide range of structure damaging observed during the past earthquake across the world is very educative and identify the structural configuration that are desirable versus those which must be avoided. So that I say that only the structural design is not important, the size and shape of the building is also significant role while the earthquake should be occurs. Now first we take the aspect size of building. So in a tall building with large height to base ratio, figure it also see what should be the height to base ratio. The horizontal movement of floor during the ground shaking is large. Now we are to take first case. Our building is tall with large height, but base size ratio is very thin. So the ground shaking is large. In short but very long building, the damage effect during the earthquake shaking are many. And the building with large plan area like warehouses, the horizontal seismic force can be excessive to be carried by the column and wall. So according these three figure, you can visualize what should be the size of our building for resisting more effectively this earthquake force. You can see the first case. It means our case A, tall building. You can see that building is very much tall and the base ratio is very much thin. So this is a significant effect during the earthquake is occur in horizontal force. Second one is too long. The base ratio is too long and height is not properly done according to maintain this base by base ratio versus height ratio. Then it should be also effect of significant. And second one is too large in plan, like our warehouses, or you can say the workshop is, seminar halls, like all this too large in plan. It means it's very large on building. So building with one their overall size much larger, much smaller than other two to do not perform well during this earthquake. So it should be a significant criteria to decide height to base ratio, and based on that we give the size or the shape of building. So that's why it should be performed well during the earthquake is occurs. Now I ask one question to all my students. According to these three shape you have to see in our figure, you have to gain the answer of the same question. Which shape in your mind are perfectly perform well during the earthquake is occurs? So write in our comment box. Also we have to discuss in a lecture 4 which shape is perfect for our RCC building. Next, horizontal layouts of building. So in general building with the simple geometry in plan, like perform well during the strong earthquake of building with re-enter the corners like those U shape, V shape, H and plus shape in a plan. Have sustain the significant damage. Many times the bad effects of these interior corners in a plan of building are avoided by making the building in two parts. So for example, the L plan can be broken up to in two rectangle plans, shape using the separation joint at the junction that will be seen in figure 2. Often the plan is simple, but the column bore are not equally distributed in plan. The building with such features tend to twist during the earthquake of shaking. So these both effects are very much severe in our building. We will see in this figure. You can see that we will build L-shape plan of our building. You can see that in between that the shape is not properly filled. Means both the corner are left. Then it should be create the separation of joint, making the complex plan into the simple plan. Now you can see the plus plan. This is the simple plan and good A. There are no generate any corner in a building, or you can say the height and base ratio are perfect. Then this is the simple plan or good plan to resist the earthquake force. We avoid that much corner. You can see in this figure. This corner are give the significant effect during the earthquake it occur. So this we will provide in a plus shape. You can see that four corners. There are the chance to separation of this different plane. You can see that. Suppose we can create a plus shape of building. So there are the separation of one part. Then it should be separate by second part, third part, and fourth part. Before the avoid this the phenomena of the separation of building, we avoid the corners, and that's why you can see that figure A. It should be a perfectly designed to resist the earthquake force. Now vertical layouts of building. As we know that what should be the height and the base ratio. Now we go further move on the vertical layouts of building. So the earthquake force develop at the different floor level in a building need to brought down along the height of the ground by the shortest path. So we know that nearer to the ground our story should be resist significant effect during the earthquake. If the building is tall, then it should be a lighter first one, and the shape should be maintained to height to base ratio. So any deviation of discontinuity in this load transferring path result the poor performance of the building. So our load transferring path should be perfectly designed, and it should be resist this all the force that will be discussed in previous two lectures and this one. So building with vertical step back, like the hotel building with few story wider than rest, cause the sudden jump in earthquake force at the level of discontinuity. That will be seen in figure 3. Now building that has forever the column or wall in a particular the story or with usually tall story tends to damage or collapse which initiative that story. But many of building with that open up ground story intend for parking collapse for very severe damage in Gujarat during the 2001 effect. You can note it down which are the buildings are more effect during earthquake when the many of building open ground story intended for parking. We have to provide the space for parking, and we will not construct the wall during the periphery of our plan, and that should be a very severe effect during the 2001 earthquake are occur in Bhuj, and it should be noted at this type of structure. We also seen in a figure also, so you can get the more idea about that plan. So the building on slopy ground have the same unequal height of column, although the slope which cause the same effect like twisting and damages shorter columns. So building with the column that hangs or float on a beam at the intermediate story and to do not all the way of the foundation have the discontinuity in the tall transfer path. Some building have reinforced concrete wall to carry the earthquake loads on the foundation. So building in which this wall do not go all the way to ground but stop upper level and are liable to get serviceability damage during the earthquake. Now you can see that all the aspect of building. First aspect, setback. What should be the setback criteria? So you can see that first figure. Our first two story are larger in plan, and after that we have to change in our story. So this inertia force of this 2 or 3 story are different, and this inertia force are different, and that's why the effect of setback. You can key that sudden jump of the earthquake force during this different story height value, it should be increased. So same the second one, if I built up a building, while in case of up to through some base period it should be at 7 or 4 height, and up to the plan of some extension it should be a 3 plan, then again this portion of building inertia force are different, and this portion of inertia force are different. Again it should be the effect of setback. Same case of the first figure, it should be inverse. Like ground story we should provide the parking, after that we should extend our plan, then again it should be the effect of setback during this earthquake. So this is the avoided upon the setback and sudden jump of earthquake force. Second one, weak or flexible story. We should provide the ground story with the parking, and we not construct the wall in periphery of plan. Then it should be a weaker story, while the earthquake it should be occur. So after the nullified this effect, we construct the frame structure completely, or you can say they will found the construction of brick infill panel throughout the plan to resist this weak story concept. Third one is for building is located on slopy ground. So you can see that some of the column are very short in a length, and some of the column are very long. Then again it should be creates the more significant effect while shaking is occur. So again the hanging of floating of column. Some column are hanging, you can see that over there. Some are again the floating, then it should be a create more in effect of earthquake should be occur. So we avoid this aesthetic point of view, but we more focus of resisting the earthquake force during this building should be designed. Second one is discontinuity structure of member. While you can see the discontinuity, you cannot clearly seen, but you can the check of discontinuity with the effect of this window. Somehow the wall should be discontinuity in plan. Why? Because for elevation purpose we set back the window and opening at a different story height should be changed for the aesthetic point of view, and it should be looking good for the architecture plan. But our load transferring system, the hierarchy should be damaged. That wall should be not transfer the load throughout this story, because you can see the uncertainty of this discontinuity of opening and door window, and that should be a significant effect of the earthquake should be resist. So these are the all forces should be danger while the earthquake resisting design is now next one is adjacency of building. That's why is very important while the land is consuming, and so much developed countries are now the high-rise building, it should be start to the construction. When the two buildings are too close to each other and they may have pound on each other during the stone shaking, with increase the building height, this collise can be greater problem when the building height do not match. You can see in this figure. So the roof of the shorter building may be pound at the mid height, and the column of the taller one, this can be very dangerous. Now what should be the done in the adjacency of building, or what should be the pound? That should be the effect of pound. While world building is larger than second one, said the column it should be shake during the earthquake forces occur, and it should be severe effect on this smaller one. So this type of significant pound we avoid when we construct the second one new building nearer to the old building. We maintain the same height of building when the construction is to be start, and we avoid this weak story concept also to signify the effect of pound, or you can say the adjacency of column. Now what should be the done? Suppose this building is earthquake resistance, perfectly done with the all phenomena or philosophy of code of earthquake should be satisfied. But this one is not earthquake resistant building, because this one is construction older one. So while the earthquake forces occur, that column should be start to the deflect, and it should be create the significant effect of older one building also. So we avoid the pounding can occurs between the two existing building due to horizontal vibration of the two building. So we maintain this one is very important while we construct the high-rise building nearer to the existing building. So this all about the earthquake resistance phenomena. So in this lecture, the main concept over the delivering the lectures are exhaustive of building. Second one is most important is inertia force of building. What is the significant effect of deformation due to column and beam also? What should be the architectural shape while we create the height and shape ratio? What should be decide of the building? That should be a very important during this phenomena. So in next lecture, still we have to continue about the design philosophy of building. Thank you, friends. If any doubt, then you have to write in comment box. Thank you. We will get soon to our lecture 4 for the same topic of earthquake resistance building.